Yeah, that's right. When n equals 1, it's pretty bad, right? Because then what you're doing is just, right? You're just taking something like this, right? That's your approximation, right? And as n gets higher, then the approximation gets better in this pretty fast way. I think the part that's probably unfamiliar to you is this bounding of the second derivative, right? I don't know if people are comfortable with that. Are people comfortable with that? Bounding the second derivative, right? Right. We know that the error is controlled by something times a bound on the second derivative, and so we have to figure out a bound on the second derivative, and we sort of we find one by using the triangle inequality. Are there any questions about how we did that? We'll do another example right after this, so don't worry if it seems a little strange, but do you have any questions right now about this? Any questions? Well, do you have a question? Yeah, okay. Anybody else? Anybody have questions? Yes, you do. That's right. Yeah, for every problem, there's going to be a different m, right? When you have to figure it out. You have to figure it out. You have to figure out an m when you're given a problem. So, like what's m? M is just some upper bound. It's just some number bigger than the absolute value of the second derivative on that interval, right? So it depends on the function and it depends on the interval also, right? So if you change the interval, we're gonna have to change m. If you change the function, you're gonna have to change m.
Well, for the first example,
yes.
You can get the exact number of second derivative of that.
Yes, exactly.
In this example, we can't get.
That's right. That's right.
But
Yeah.
we do it for our convenience.
I mean, so if you wanted, maybe what you could do is say, figure out where the maximum value is.
Yeah,
right.
It's difficult.
Yeah, so you'd have to do some calculus 1 technique, right? You have to take the derivative, see where the derivative is 0, find the maximum, the minimum, and you see where the absolute value is biggest, right? But we're not going to do that. Okay, we're gonna be a little bit sloppy. So this is a little bit sloppier than what we did over there, because over there we got exactly the second derivative. Here we're not getting exactly. This isn't the best. This isn't really the best upper bound. This is just one upper bound, right? But it's good enough for us. We can use it. But it's not the best upper bound. Let's do another example. Let's do another example. So, okay. So going back to the one we talked about at the beginning, e to the negative x squared. Okay. So now let's ask, what's the bound? What's e sub n? Or what is determine a bound on the error. Determine a bound on the error. Okay. So again, we need to take the second derivative, right? So the first derivative is going to be e to the negative x squared times negative 2x. Right. The second derivative is going to be negative the first guy times the derivative of the second guy plus the derivative of the first guy times the second guy. Right? So we get negative 2e to the negative x squared minus 4x squared e to the negative x squared. Now plus. Right. Okay, so just taking the derivative. Right, okay, and so now let's try to get some bounds, right? Let's try to bound this thing, right? Let's try to bound this thing for x between 0 and 10. Okay, maybe I'll let you do it. Take 1 minute and get some number, get me a number that's bigger than this function on this range. Okay, turn to somebody nearby and say, the number I got is whatever number. Five, 100, 1 million. Yes. Yes, go ahead. Yeah.
How to draw the image of the x?
How to draw the image of e to the x?
Yeah.
Okay. The function e to the x looks like this, right? Right. Right now we're dealing with e to the negative x squared, right? E to the x squared is going to go faster than that, right? It's going to be faster shrinking, faster growing and faster shrinking.
It doesn't matter.
Right. But we have negative, right? So it's going to be the opposite of that. Right. It's going to be like this.
How we determine which number is the maximum because the two factors, one from what the original term it goes up and the other is goes down from each term.
Yeah. So maybe you don't want to do it all together, but you want to break it up into pieces, like what we did over there. Yeah. So, maybe one trick is to use the triangle inequality again, break it into two pieces. Did anyone get a number? Not yet, but you're about to. Okay, good. I'll give you one more minute, and then you can call me.
I'm still confused with
Yeah.
If I divide it into two parts,
Yeah,
this
yeah.
part is
Yeah.
still like this one goes up, this one goes down, and I cannot determine the maximum this fraction.
Yeah. So maybe you need to divide it up into further parts.
I mean, do I need to take the derivative of this one? and-
You could, but we're going to do something even more crude than that. So we're not going to be very careful about it. Okay. We're basically going to just take absolute values. You're going to break it up into smaller and smaller pieces, and then just take the maximum of each piece. Okay. Who has a number? Okay. Okay. In that case, I'd like you to talk to somebody just for a minute. Okay. Talk to somebody nearby and say what you're doing. How do we generate what? F?
F in the equation.
What's F?
No, M.
M?
Yeah.
That's the question. That's what I'm asking you to do. Okay. Does anyone have anything to say? How about Chen Xiang Li? You don't know? Okay. How about Zhang Shiqi?
Because 1e is 0.
Yeah.
Negative to e to negative x squared has the max value is negative 2. Oh, it's 2 because
Yes.
that's absolute value.
Yeah. Okay.
And,
Yes. And then?
and then that part,
Yeah.
because 1x is 10,
Yes.
it got the max value,
Yes.
and times 1.
Exactly. Right. So you get 402, right? 402 is the answer. Is one answer. Okay. So you say, okay, let's use the triangle inequality again, right? This is smaller than 2 e to the negative x squared plus 4 absolute value of x squared e to the negative x squared, right? So you just break it up into pieces. Right? Is this okay or is this not okay? Right. So let me do it a bit slower. So you say, okay, I'm going to break this up into two pieces: 2e to the negative x squared plus 4x squared e to the negative x squared. Okay. Right. You know, it's always true that if you take the absolute value of the sum, that's smaller than the sum of the absolute values. The triangle inequality. Right, the triangle inequality. Okay? Okay, and you also know that the absolute value of a product equals the product of the absolute values. Right? So that's just how the absolute value works. Right? So here we're going to get 2 times the absolute value of e to the negative x squared plus 4 times the absolute value of x squared times the absolute value of e to the negative x squared. Okay, right? And then you say, let's just take the maximum of each of these pieces individually, right? E to the negative x squared is biggest when x is 0, when x is 0, we get 1, right? So we know that this thing is small, that first piece is smaller than 2, right? We know this is smaller than 1. We know that x squared has its max when x equals 10. Okay, this is how you get around the trouble that you were pointing out. You're saying that, well, as you head towards 10, this piece gets bigger, but this piece gets smaller, right? So we're just gonna avoid it. We're gonna say, let's take this piece when x is 0, and this piece when x is 10. That's certainly gonna be bigger than this, right? So you say, okay, you get 4 times 100.
The answer will be much bigger than the
Yes.
Then the n you get is not really accurate.
That's right. This error is not that accurate. Okay, but it still gives us some control over the error. Okay, so that's why I said determine a bound on the error. But so I mean, if you want, you could be more careful about it and take the derivative of this and find out where the max and min occur, and then use that. But I'm not going to ask you to do that. I mean, if you want to do that, you can, but that's going to be a lot more work. In fact.
If you find zero geometry, it's actually not harder because it's too long.
Yes, it will be a pain.
But how how you can like choose x equal 10 for the like first part, and then you choose x equal 0 for that. You should choose the same never.
Why do you have to choose the same point? Why do you have to change it? It's just
I'm really choose the different x.
so let me say it like this. Suppose you have two functions, f and g. Okay, and somebody says, I'd like to know, I'd like to get a number that's bigger than the product. Okay, I'd like to get a number that's bigger than the product. Okay, well, this is equal to this, right? And suppose you know that g attains its maximum value somewhere, right? This is g's maximum value, this is g, and then f, right, attains also some, make it positive just to make it easier. F also attains some other maximum value. Okay, at a different point, shoot. At a different point. Okay, so you certainly know that that the product is smaller than m times n, right? The product is going to be smaller than m times n because you know that the biggest f could be is n, and the biggest g could be is m,
I
right?
understand that one, but I just feel like the answer you get is not accurate.
That's right. So you lose some degree of accuracy. You lose a little bit on the constant, right? But you don't really care too much because what you're really concerned with is, as n gets bigger, that constant doesn't matter that much, right? And that constant, the main thing is that the error decreases like 1 over n squared, right? So you've got this constant. Maybe instead of 402, the real constant is 100, but that's not really the point. Right? The point is that as n gets bigger, you can get this as fine as you want, right? Okay. But you're right. It's not the best answer. You're right. You're absolutely right to say it's not the best answer. Okay. So what our bound is then is 10 cubed over 12 n squared times 402.
X equals 10, yeah.
Mm-hmm. Right. B minus a is 10. Right. B minus a, the length of the interval is 10.
I mean, the bond.
the bound here.
Why is
Why is it 400? Because we took, what's the biggest x squared could be? 100, right? What's the biggest this could be? 1. 1, right? So this thing is smaller than, this thing is smaller than 400, and this thing is smaller than, it's bounded by 2, right? So the total bound is going to be 402. So you get this, the number is huge, right? But, as this will allow you to control the error however you like. So if you want, if somebody says, I'd like my error to be smaller than 0.1, right? I want my error to be smaller than 0.1. You just choose an n big enough that this thing is smaller than 0.1, right? If you want your error to be smaller than 0.001, just choose an n so that this thing, is smaller than 0.0001, right? And then do your trapezoidal approximation. So the good thing about this is that you can make your approximation as good as you want, right? So if somebody says, I'd like to have this, with 100 units, 100 degrees of accuracy, right? Then you can 100 digits of accuracy. Then you can do it. Right? You just need to figure out what n you need, and then you do the calculation. Right? You ask your computer to do it. Okay, so let's there's another kind of approximation called parabolic approximation. Okay, so you notice that what we did, right? Also called Simpsons approximation, after the person who did it. So the idea is to divide the base into 2m pieces. Okay, so your number is always going to be an odd number, an even number. Then approximate with quadratics on every 2 subintervals. Okay. So the picture is like this. You have some function, and you divide into an even number of pieces. Okay. So let's say we take eight pieces. Okay, and then so x0, x1, x2, x2m. And then at each point, again, we get the height, right? And those heights are again y0, y1, y2, etc., etc. Okay. And the point is that whenever you have three points, then you can approximate with a quadratic, right? 2 points determine a line, 3 points determine a quadratic, right? So you take a quadratic, you find whatever quadratic function approximates those 3 points, right? So you find whatever quadratic function approximates those points, and then, right, and then you take the area under that quadratic. Okay, and that's going to be your approximation. Okay. It turns out that the area is actually going to be b minus a over n divided by 3 times y naught plus 4y1 plus y2 plus 4, oops, plus 2y2 plus 4y3 plus 2y4 plus blah 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 plus 2y n minus 2 plus 4y n minus 1 plus y n. The reason is the following. So why do you get this formula? I'm just gonna let me sort of briefly say. If you have a parabola that looks like this, negative h 0. Sorry, where h is just some length. Okay, where you have a height y naught, y1, and y2. Okay, and you make a parabola that goes through it like this. Then the area underneath P turns out to be h over 3 y naught plus 4 y1 plus y2. Okay, so don't worry too much about it, but this is why this happens. See, what you get is, and this is b minus a over n times y naught plus 4y1 plus y2 over 3 plus y2 plus y plus 4y3 plus y4 over 3 plus yn minus 2 plus 4y n minus 1 plus y sub n over 3. Right? In other words, it's just the areas, it's the sum of these areas. just to give you some sense of how this formula turns up. Right? What is this 1, 4, 2, 4, 2, 4, 2, 4, 2, 4? Right? It's because of this. And further, we also have an error estimate for this procedure, which is that if the fourth derivative is continuous on AB, then the difference between the function, the actual, and the approximation is controlled by b minus a over 180, b minus a to the fifth over 180 times m over n to the fourth, where m is the maximum of the fourth derivative on AB. So we have something, along the same lines as the trapezoidal rule, but you see that the error here gets smaller a lot faster, right? The error here gets smaller, like 1 over n to the 4 instead of 1 over n squared. So there's some advantage, as you might expect. This is going to do something better because you're using second order approximation rather than just first order approximation. Right? You're using parabolas rather than lines. Any questions about this? So again, if you were playing the game, if somebody says, what n do I need to make my approximation within 0.01, say, then you do the same sort of thing. You would take your function, you take the fourth derivative, and then you try to find some bound of the fourth derivative, and then use that here, and then figure out what n you need to be smaller than, to make the error smaller than whatever is desired. Well, you look like you have a question. Do you have a question?
Will you choose the method over this one?
I'm sorry?
I mean, which method would you choose if you determine
Which method will you choose?
I mean, this one or the one you just introduced?
Yeah. So,
Because for this one, you need to figure out the SN, right?
yeah, but it's not that hard, right? It's just as easy, right? You don't have to make this function. All you need to do is evaluate the values at points, right? You just say, right? So, for example, if somebody says, I'd like to, what is natural log of 2? What is natural log of 2 within 0.01 error? So here's the problem for you. What is the natural log of 2 within 0.01 error? Okay, and you don't have a calculator. You don't have a calculator for some reason. Okay, so So you'd say, okay, well, I know that the natural log of 2 is the integral of 1 over t between 1 and 2, right? So what I need to do is approximate this, right? And I need to approximate it well enough that my error is smaller than 0.01. Okay. So, so what would you do? You'd say, well, okay, so my function is 1 over t. If I take the derivatives, right, so t to the negative 1, I get negative t to the negative 2, 2 to the negative 3, right, negative 6 to the t to the negative 4, I get 24 over t to the 5th, right? That's my fourth derivative, right? And I know that on 1, 2, the maximum occurs at t equals 1, right? So the max is 24, right? The maximum value of my fourth derivative is 24. And so what do I know? My error then is controlled by b minus a to the 5th over 180 times 24 over n to the 4th, right? So 4 over 30, let's say 2 over 15.